So the second 1.3 video is going to talk about symmetry of functions. Symmetry is something that we can see visually if we are looking at a graph. We're also going to look at how to determine what the symmetry is based on an analytic analysis, meaning we're going to plug in negative x and be able to do it with an equation is what analytic is, okay? All right, so the graph of an equation is symmetric with respect to the y-axis if for every point xy, the point negative xy is also on the graph. Okay, in other words, if you have a point to the left of the y-axis, there is a point with the same y value to the right. So if I have a point over here at -2, I don't know, 5, then that means there's also a point at +2, 5. Okay, to test for this, we can plug negative x into our equation, and if we get the same expression out that we started with in the equation, then we have an even function. Okay, I'm sorry, we have symmetry with respect to the y-axis, which is called even. I think the even thing comes up down below. All right, and then we have symmetry with respect to the x-axis if for every point on the graph, x negative y is also on the graph. So this means if we have a point above the x-axis, so let's say at 1, 2, we also have a point at 1, -2. Now note, unless you have points that are only on the x-axis, this is never going to be a function. Doesn't mean it can't be an equation, okay? Like we could have x equals y squared, could pass through points like that, not 1, 2, but some points like this. But we can still determine symmetry, okay? So if you plug negative y into the equation and you get the same expression for x out, or the same expression for y out, then it is symmetric with respect to the x-axis. And then we have some symmetry with respect to the origin if for every xy, the ordered pair negative x, negative y is also on the graph, okay? This one, when we say symmetry with respect to the origin, this is rotational. So this is if we rotate the graph halfway around 180 degrees, it lands on itself. Okay, so an example of that would be something like y equals x cubed that looks like this. If I rotate that around 180 degrees, this part points down and this part points up and it's right on top of itself. Okay, or an ordered pair, I could have a point here at 2, 8. I also have a point at -2, -8. Okay, so let's start by looking at these equations to determine if we have symmetry with respect to the x-axis, the y-axis, the origin, more than one or none. Okay, so remember the test, we can plug in negative x or y values, or both, okay, to determine symmetry. So let's start by plugging in a negative x. Okay, so if I plug negative x in place of x, I have this. Negative x to the fourth is the same thing as x to the fourth because -1 to the fourth is +1. Or in other words, we're raising it to an even power. So y to the fifth equals x to the fourth plus 2, which is exactly the same as what we started with. So that means that this does have y-axis symmetry. Okay, if we plug in negative y for y, then we would have negative y to the fifth equals x to the fourth plus 2. That is not the same because negative y being raised to the fifth power gives us a -1 coefficient. Not the same, so we do not have symmetry with respect to the x-axis. If we plug in a negative x and a negative y, I'll go ahead and write this out, but we can see that we're going to end up with the negative y to the fifth on the left, but x to the fourth will be the same on the right, so it doesn't have that symmetry either. So this just has symmetry with respect to the y-axis. Okay, y equals 2x plus 5. If I plug negative x into that, I get y equals -2x. I'll have 2 times negative x plus 5, which is not the same as the original, so no y-axis symmetry. If I plug in a negative y, well, that just changes the sign here, so no x-axis symmetry. If I plug in a negative for both, I have negative y equals -2x plus 5. This almost looks the same as the original equation, but I don't have anything to change my sign on the 5. Or in other words, if I divide the whole thing by -1, I would have y equals +2x minus 5, which is not the same. So this has no symmetry. Okay, this one, x equals y squared minus 2. If I plug in a negative x, then I just have a negative x there, the opposite of the original. So it does not have y-axis symmetry. If I plug in a negative y, though, because it is being squared, I get the same thing, y squared minus 2 out. So this does have symmetry with respect to the x-axis. And then if I plug in negative x and negative y, I already know this one's going to come back as the same. This is going to be, positive y squared, but this one will be the opposite. So it does not have symmetry with respect to the origin, because it would be this, and that's just y squared. Okay, so x-axis symmetry is the only one. This one, hopefully you recognize this as the equation of a circle that's centered at the origin. But if I plug in, so let's do negative x. So I'd have negative x squared plus y squared equals 49. That's the same as x squared. So yep, that works. Also, if I plug a negative y in here, that one's going to work. If I plug a negative in both spots, this is the same thing as the original because that's an x squared, that's a y squared. Okay, so this actually has all three symmetries. Okay, which makes sense because it's a circle and we can rotate it or flip it however we want and it'll still be in the same spot. Okay, even and odd functions. I think I mentioned this earlier, but we hadn't gotten to it yet. So if a function is symmetric with respect to the y-axis, then we say that that function is even. And if it is symmetric with respect to the origin, so in other words, the 180-degree rotation, okay. So those are the two things we're looking at when we visually see the graph and are trying to determine even or odd symmetry. There is no fancy name for symmetry with respect to the x-axis because it doesn't happen with functions, so we just don't care about it that much. All right, so this first one, if I were to take this and rotate it 180 degrees, this part right here would land here, this part would land here, so this one is odd. Please pause it, try the other three, and then resume and see if you got the same thing I did. This one, I can fold on the y-axis, so this is an even function. It has symmetry with respect to the y-axis. This one has neither, because if I rotate it, it would land down here. If I fold it, it would land over here. Okay, and then this one right here is another odd function because I could rotate it 180 degrees. This part would land here and vice versa. Okay, normally though we don't have the graph of a function or we don't have something that's like a basic parent function, so we need to be able to evaluate algebraically to determine if a function is odd or even. So the way that we do that is we plug negative x into the function and evaluate that. If we get the same original expression out, so if we get the same f of x out, then we have an even function, okay, because remember that symmetry with respect to the y-axis. If we get the opposite out, then we have an odd function, okay? In other words, if I get an expression where I can factor a -1 out of the whole thing, and this matches the original f of x expression, then I have an odd function. Okay, so for this one, I'm going to evaluate f of negative x and compare it to the original. So I've got negative x squared plus 6. This is an even power, so that's x squared plus 6. This is the same as f of x, the original function, so therefore I have even symmetry, which is with respect to the y-axis. Okay, I would pause it, try the last two, see if you get the same thing I do. For this one, I'm plugging in negative x to g, so I have 7 times the quantity negative x cubed minus negative x. So negative x cubed is just negative x cubed, so that's going to be a negative 7 x cubed plus x. I'm going to factor a -1 out of that whole thing and show that this is 7x cubed minus x, which is equal to the original expression. So this is negative f of x, g of x. So since g of negative x equals negative g of x, this has odd symmetry or symmetry with respect to the origin. Okay, and then last one here, again, plugging in negative x. To the fifth plus 1, which is negative x to the fifth plus 1. If I factor out a negative 1, I have x to the fifth minus 1, which is not the opposite of or equal to the original function, so this one has neither. Ooh, there's an e in there.